Hi, everyone. Welcome to the quantum computing seminar. Today, Walker H. Stern is going to be introducing symmetric monoidal categories. Take it away, Walker.
Thanks very much. So this is very much following on from my first talk. I'm going to try to make this one a little bit less intense, perhaps, than the previous one. And I will say, when dealing with monoidal and symmetric monoidal categories, there are a lot of technical complexities that one does technically have to deal with. However, I'm going to be brushing a lot of those under the rug today and focusing on the pieces that we'll need to really work with them as we delve into categorical quantum mechanics. So there are going to be 3 guiding examples throughout this talk, and there will really only be 2 that I'll talk about a lot. But I want to introduce the third because it acts as a very nice toy model for a lot of the structures we're going to explore in the next 3 or 4 talks. So firstly, we have the category, which I'm going to be denoting F-Hilb, following the Vicary Heunen book. And it has objects which are finite dimensional Hilbert spaces, and morphisms which are linear maps. Now, I want to make a brief remark here because this is actually kind of a weird category to consider. If you consider the category of finite dimensional Hilbert spaces with linear maps, because these linear maps don't remember anything about the Hilbert space structure, this is actually equivalent to the category of finite dimensional vector spaces. And so a category theorist looking at this definition might say, that's clearly the wrong category because it doesn't remember the structure that you claim to care about. However, as these lectures go on, we're going to be defining additional structures on this category that do explicitly rely on the Hilbert space structure. And so in that way, we're going to be, we're going to be changing this to be a little bit more sensible as a definition. So if that was confusing to you, don't worry. There actually is going to be Hilbert space structure actually coming into play. So then the second guiding example is the category set. And the objects here are sets, and the morphisms are functions, or maps, if you like. And then the third, and this is one that we haven't yet seen, is what's called rel. And the objects are sets, but now the morphisms, a morphism from X to Y, and I'm going to denote morphisms in rel with a slash to distinguish them from morphisms in set, are R, where R is a relation, that is a subset of the Cartesian product of X and Y. So I've claimed that this is a category. Let me very briefly explain why, because if I tell you this is a category, I need to tell you how to compose morphisms, and I need to tell you what the identities are. So maybe sidebar, given R and Q, relations respectively from Y to Z and X to Y, define R of Q to be the set of, well, it has to be pairs, XZ in X cross Z, such that there exists a Y in Y with XY in Q, YZ in R. So this is the composition, and the identity on X is just going to be the set of pairs XX for X in X. The diagonal, if you will, of the product of X with itself. And so this is a well-defined category, and then the last thing that I want to mention about this before moving on is that in this category rel, you actually have all of the category of sets. So given a function f from x to y, a morphism in the category set, we can define its graph, which is a relation gamma f subset x cross y, just defined by, well, what you would usually expect the graph to be. It's those pairs x, f of x, with x in x. And a function is uniquely determined by its graph, and it's not hard to check that these graphs compose in just the same way that the functions originally would have composed. So this really does define a functor. Also, this is the graph of the identity, if you like. This really does define a functor from set to rel, and this functor doesn't forget any information. Okay, so with that sidebar out of the way, let's come to the main idea of today's talk. Is defining multiplication operations on categories. And let me put multiplication operations in scare quotes because it's perhaps a little more complicated than that. And we can start out with some examples. So firstly, in set or rel, doesn't really matter which, given objects, so sets, x and y, we can define their Cartesian product, x cross y, which is, again, just the set of pairs. So this is a way of taking objects in a category and multiplying them. And now, in finite dimensional Hilbert spaces, we have a couple of options. Actually, in set or rel, we also have a couple of options, but let's think about this. In finite dimensional Hilbert spaces, given v and w in the objects of, we can either take the tensor product, v tensor w, and formally this needs to be equipped with an inner product. So we say that the inner product of v tensor w with v prime tensor, those are all going the wrong direction, aren't they? Yes. It's been a while since I've used physicist notation, almost a decade. So this is really just v prime times w prime. And so this is our Hilbert space structure.
The first one you go the other direction, you put a diagram of the first one.
Well, I want this to be like you're defining an inner product where this is a vector and this is a vector. I'm not yet identifying anything with covectors. When I talk about dual spaces, I will actually identify covectors. But okay, or we could take just the direct sum. Now, I'm not going to talk about this today, even though it fits into the framework that we're going to be discussing today. It will come up again when we discuss biproducts. So we can forget about that and stick with the tensor product and the Cartesian product. And in both cases, or let's say all three cases, we can also multiply morphisms. So in set, so let's say, actually, given f from A to B, g from C to D? Well, firstly, in set, what should f times g from A times C to B times D be? What should it send AC to? Yes? Yeah. F of A, G of C. And in finite dimensional Hilbert spaces, what should F tensor G do? Well, here, because of the way we define the tensor product, it's easier to just say what it does to a generating element. And once again, it's just going to be basically the same thing. F of A tensor G of C. So we act on this pure tensor. Now, it's in rel that things get a little stranger. So now I'm going to rewrite these as, let's say, R from A to B, Q from C to D. And now we want something that's like R times Q that goes from A times C to B times D. So it's going to be a subset. R times Q will have to be a subset of A times C times B times D. So what is this subset? Well, it will look basically like the Cartesian product, but we have to switch the order around. So this will be some AC, B, D, AC, B, D, such that A, B is in R and C, D is in Q. And I'm not going to check on the board right now, but you can very easily verify for yourself that all of these define functors. So for instance, the Cartesian product defines a functor from set times set to set. And the tensor product defines a functor from finite Hilbert spaces to finite Hilbert spaces, or finite Hilbert spaces times finite Hilbert spaces to finite Hilbert spaces. So we have some nice sort of multiplication operation structure. And I don't know about the rest of you, but when I see something that looks sort of like a monoid or a multiplication operation, there are effectively 3 questions that I ask myself about it right off the bat. So these natural questions are, well, are these associative? Unital? Or commutative? And you might be looking at that list and thinking, there's one you left off. Can you invert things? The simple reason there is inverting things in this framework is much rarer than these 3 properties. And so we're going to focus on these 3. So let me just say very briefly what I mean by this. So associative should mean something like A times B times C is A times B times C. Unital should mean there exists some I such that for any A times I equals A equals I times A. And this marker is dying, so let me switch to a better one. Commutative should mean that A times B is always equal to B times A. So quick show of hands. Let's focus first on the Cartesian product on set. Is the Cartesian product on set associative? Yes? Anyone say no? Is it unital? Is it commutative? Okay, what about the tensor product on finite dimensional Hilbert spaces? Is it associative? Unital? Commutative? Okay, I have been a little bit mean and posed a trick question. The answer to all 6 of those is no. Now, it's no in a very technical sense, but morally it's right. And part of what we're going to be doing today is untangling why morally it's right. So the reason that the answer is no is, let's look at first associativity. A cross B cross C is the set of A, B, C. It's a set of pairs consisting of an element and a pair, A in A, B in B, C in C, and A cross B cross C is a set of pairs where the first thing is a pair and the second is just an element. So these are not technically equal, but they are morally the same. And similarly, A cross B is the set of AB, A in A, B in B, and B cross A is the set of BA, B in B, A in A. So again, it's a bit of a mean bait and switch. In any reasonable moral way, you look at these and you say, yes, of course they're associative, unital, and commutative, but on the very technical level, they're not. You have to actually do something to, say, commute these past each other. So the way that we end up formalizing this is we say, not that they're commutative on the nose or associative on the nose, but that they are weakly commutative, associative, or unital. So formally, what this means is we have isomorphisms that display the unitality, associativity, and multiplication. So we have an isomorphism that I'm going to call alpha ABC. And this just does precisely what you'd expect it to. It sends a pair consisting of a pair and a single element to a pair consisting of a single element and a pair. Just moves the parentheses around. And we have, so when I write an asterisk, what I mean is the singleton set, the set with a single element. We have isomorphisms, which I'm going to call lambda A. The lambda here stands for left, because we're multiplying on the left. Rho A for right. And again, these just do exactly what you'd expect them to. They forget about your singleton and remember the element. And so these are both clearly isomorphisms. And we have what I'll call sigma AB. And sigma doesn't stand for anything. So alpha stands for associator, lambda stands for left, rho stands for right. Sigma I don't think stands for anything. It's sigma because you write permutations as sigma. That's a very good point. You are almost certainly correct because the symmetric groups are also capital sigma. Yes. Okay. Now I do know why. So we have these isomorphisms. And these tell us not that these things are equal, but how we can canonically identify them. And it turns out that these fit into a very nice, very general sort of structure. And so this nice general structure is going to be our first definition of the day. And I'm going to divide this board in half because this is a long definition. A monoidal category is a category C together with a functor which I'll write using the tensor product symbol from C cross C to C, called the monoidal product. Now, some references will also just call this the tensor product. I find that confusing because the tensor product of vector spaces or finite Hilbert spaces is a special case of a monoidal product. Isomorphisms alpha A, B, C from A tensor B, tensor C, to A tensor B, tensor C in C, called associators. Isomorphisms. Sorry, whoops. I need to say that we have an object first. An object, usually denoted by a capital I in the object of C, called the, again, monoidal and I should say, this word monoidal is cropping up. Basically, this is like a monoid. You have a multiplication that's sort of associative and unital, but not quite, so you stick an AL on the end. Isomorphisms. I tensor A, lambda A, rho A tensor I, called left and right unitors. And now I left this gap here because what we really want to talk about are symmetric monoidal categories. And so the data that I've written down here are what you need for a monoidal category. But for a symmetric monoidal category, you need another piece of data, namely isomorphisms sigma AB from A tensor B to B tensor A, called braidings. So these reverse your factors, your tensor factors. And then I've given you a whole host of data, but technically, this isn't quite the definition because it needs to satisfy some conditions. So, such that any morphism built out of identities, composition, tensor product, lambdas, rows, alphas, oops, that's the wrong color. And sigmas only depends on the underlying permutation. And don't worry, I'm going to explain what I mean by this in just a second. So, a symmetric monoidal category is a category with a bunch of data satisfying this extremely strong condition. So what does this really mean? It means that if you have a bunch of objects multiplied together, maybe some of them are identities, some of them aren't, then there's only one way to get from that product to another version of that product using only these data. But this depends on the underlying permutation is because we can switch the order of objects, and we don't want that the way of getting from a tensor A to a tensor A, given by sigma AA, is the same as the identity, right? It still should flip the factors. So, for instance, this tells us that this really does act sort of like the symmetric group. So we have A tensor B to B tensor A. This is sigma AB. We can go through sigma BA back to A tensor B. But we can also get from here to here with an identity. And the underlying permutation is we've flipped and then flipped back. So both of the underlying permutations agree. And by this condition, these have to be equal. So if you compose sigma BA with sigma AB, you have to get the identity. And similarly, let's say you have I tensor A to A tensor I. This is our sigma AI. And both of these now go here by the left uniter and here by the right uniter down to A. Well, the underlying permutation is just everything collapses to A. And so this has to commute. So what this is really saying under the hood is that it doesn't so much matter if you identify things that are identified by these isomorphisms, because there's always a unique way to get from one to the other. And so you can reasonably drop copies of I, or permute things, or associate parentheses, because in the end there will only be one isomorphism that you can build out of these data that gets you from one to the other, and so that's automatically baked in. Now, the other question that this definition might raise is, this looks like a really strong condition. Anything that you can build out of all of these will always be the same so long as the underlying permutation is the same. How on earth would we prove that? Well, there's a theorem that I'm not going to get into right now. It's called McLean's coherence theorem. And it says that if you check basically the commutativity of three diagrams, you can prove that this will hold. So, in fact, there's a very finite set of checks that you need to do to guarantee that such data will satisfy this condition. Now, again, I'm not going to really get into it because for the most part in this seminar, we're just going to work with things that are well known to be symmetric monoidal categories, and we're never going to check that something is a symmetric monoidal category. But I would strongly encourage you to look at it. It's a really neat proof. It appears, let's see, where does it appear? There's a version of it in Categories for the Working Mathematician, Saunders MacLean's book on the subject. So this property that basically it doesn't really matter is sometimes called the coherence of this symmetric monoidal category. And what does coherence buy us? Well, coherence tells us that we can draw pictures. So coherence tells us that there's going to be a canonical way to interpret a picture that represents a morphism. So let me A mu B C F G. I claim that this picture represents a morphism and that it is coherence that allows us to understand this as a morphism in a symmetric monoidal category. So let me first briefly try and introduce some sense of how you might read such a thing. So I should probably label all of my objects. That would be a good idea. A, C, D, E, N, M. Okay. So firstly, we read from bottom to top. I should say, this is the convention in the book we're following. I hate this convention because in no natural language that I know of does anybody read from bottom to top. One can read from left to right or right to left, but pretty consistently we read top to bottom. However, this is the convention. It's not an uncommon one in the literature, and so we go this way. So these are going to be objects. And we additionally fixed some conventions for how we interpret morphisms. A box is a morphism. And a line labeled, say, AA is the identity morphism on A. And then there are two formal rules for reading further, and then we're done. Those two formal rules are, first, things next to each other are, let's see, tensored, are products, let's say. And second, things vertically above are each other are compositions. So just from that, we can take this picture and we can say this should represent a morphism from A tensor B, tensor C, tensor D, tensor E to A tensor N tensor M. And already you can see where coherence plays into being able to use these diagrams. I haven't bracketed this. And so, in principle, such a morphism will depend on the bracketing. But I know that any bracketing I choose is just going to be related by one unique morphism built out of these associators. So it doesn't matter. And then you might also notice one further strange thing. There's a gap here. We have a morphism, it has an input and no output. A gap is just a copy of the unit object. So, with all of that in mind, let's try to interpret this diagram. First, let's just think about this part, because it's just involving a tensor. So what this tells us is we have some morphism mu. We're given some morphism mu that goes from B tensor C to M, some morphism F from D to N, and some morphism G from E to the monoidal unit. And what we get is just the tensor product of these. We get mu tensor F tensor G that goes from B tensor C tensor D tensor E to M tensor N tensor I. And then if we enlarge our diagram a little bit so that we now add this N and M, well, we've permuted the two copies of N and M. There's precisely one way to do that. We have to use this, I erased it, sigma. So what we get is sigma AB tensored with, well, we have to do something to this I, so just the identity on I, composed with mu tensor F tensor G. But then, really, we want to treat this I as going away, right? We left it blank for a reason. So really what we then need is identity on, that's not AB, that is, yeah, no, that is MN, thank you. So identity on N, tensor the right associator on M, composed with that. And here's another place where we're implicitly using coherence. I could have gotten rid of this copy of I before twisting. And a priori, there's no reason that that should give us the same thing. But because we have this strong coherence property, well, it turns out that it all works the same. And then finally, the whole diagram is just going to be the identity on A tensored with this whole thing. Now, this, I would like to think, illustrates one of the reasons that we really like using these string diagrams. If I look at that, I can tell you already exactly what's going on under the hood. If I look at this, it just looks like a mess. It's a lot of notation to unpack, and we can't really follow through very easily what's going on. Now, the other reason that we like string diagrams is it turns out diagrams like this just sort of show up all over the place. As we've already mentioned, we're going to be making use of them in quantum mechanics, or more generally, I guess, quantum computing. Anyway, so we can now interpret these diagrams so long as we really are working in a symmetric monoidal category. And there are also things that we can do. So, for instance, we can drag things past each other. F, G. Any way that we break this up is fine, right? We can think of this as, let's say that this is A, B, C, D. Any way we break this up is fine. So we can think of this as F times the identity on D composed with the identity on A times G. Or we can redraw our diagram, and we can think of this as the reverse. F times an identity on C, G times an identity on B, and then compose. Or we can think of it this way, where we're just taking the tensor of F and G. And similarly, we can drag pieces of the diagram around so long as we don't reorder the objects. Now, once again, this is a somewhat complicated framework, and it really rests on the coherence of these monoidal categories. To actually prove that string diagrams give you this nice, unique representation of morphisms is not actually a trivial matter. You have to do quite a lot of work to prove that this is a notation that will always represent something canonical in your symmetric monoidal category. But for our purposes, it's going to be good enough to know that it works. So for the rest of today's talk, however long that is, good, I still have some time. For the rest of today's talk, I'm going to be talking about how we use string diagrams to give definitions and to prove things. And at the same time, I'm going to be giving some background on a particular definition, what are called dual objects, which are particularly useful in the categorical quantum mechanics that we're going to be considering. And don't worry, now having gotten the formal definition out of the way, we're going to go back to looking at some of our examples. So our first definition let's let C, tensor I be a monoidal category. So this is the usual notation when one's talking about a monoidal category. You'll remember there was a bunch more data that went into this. You just sort of forget about it and you only write these three pieces with the associators and uniters implicit. So let this be a monoidal category, and let L and R be objects of C. We say L is right dual, left dual to R, and R is right dual to L if there are duality data. That is, a morphism eta that goes here. This should be RL. And I'm usually just going to follow your book's notation and draw this like this, or usually. Sometimes I'm going to. So instead of this, we fix a new notation for this particular string in the string diagram. And epsilon from, which again, we're usually going to draw that way, such that this is L, R, L, and so now I'm going to briefly unpack this definition off to the side, just to explain why it is, again, much nicer to draw things this way than it is to try and write this out in standard symbolic notation. So we have eta from the unit to R tensor L, and epsilon from L tensor R to the unit, such that, well, I need to write down what this is. So this is L, but then I need to add an identity here, a unit, because that's what this takes as input. So to L tensor I, 2, so this is rho L inverse, and this goes to L tensor R tensor L, and this is the identity on L tensor eta, and this goes to I tensor L, and this is epsilon tensor the identity on L, and this goes via the left uniter to L, and this has to be equal to the identity on L. Beg pardon?
In the middle there.
Yes, you're right. So technically, very well caught. Yeah, yes. The 2 sigma L R tensor L, L tensor R tensor L to I tensor L to L. This is now lambda L, and this is epsilon times the identity on L.
Sigma
Hmm?
Sigma is alpha.
Yes. Sigma is alpha L R L inverse. And this has to be the identity on L. It's much nicer to draw this picture than to write that down. I'm not going to write the second one down for precisely that reason. So this is our notion of duality, and before we go any further, let's try and think about some examples. And again, we're going to focus on these first 2 guiding examples of symmetric monoidal categories. We'll first talk about set, and then we'll talk about finite dimensional Hilbert spaces. So in set, if L, we also write L is left dual to R. If L is left dual to R via eta and epsilon, well, then we have precisely this diagram where now I'm going to suppress the associator but leave everything else the same. To this should not be I, this should be asterisk now. 2 asterisk times, sorry, little too overeager, times L to L. So we can trace through what this is going to do. It will send an element L to the pair consisting of L and asterisk. Now, eta just picks out 2 elements. So this will get sent to L, eta 1, eta 2. And then this will get sent to asterisk, eta 2. And this will get sent to eta 2. But this has to be the identity. So this implies L is a singleton set, eta 2. If you trace through the other condition, you'll see that R also has to be a singleton set. So this is not very promising. We've made a definition, but we tried to understand it in set, and it tells us there's exactly one example up to isomorphism, which is the singleton set. Not very good. So let's try again. In finite dimensional Hilbert spaces. So here, things are a little bit better. So if we have V in finite dimensional Hilbert spaces, we can define the linear dual as a vector space to be just the set of linear maps from V to C. And we get an isomorphism. And in this case, this isomorphism is really canonical because it's given by the inner product here. This is going to send V to what I'll call V. And this is the functional from B to C, which sends W to VW. And we can use this to put an inner product on V star, namely, well, the inner product of V with W will be, let's see, W, V, so V, W, complex conjugate. Actually, Selman, you can perhaps answer this. What's the physicist notation to use for complex conjugate?
You put a bar over it?
Yeah.
Yeah.
Okay, so that's the good one?
Yeah.
Okay, excellent. So this gives us a Hilbert space structure. And so we have this canonical dual Hilbert space. And now if we fix a basis of V, we get the dual basis of V star. And so we can define eta, which is now going to go from C, the unit of the tensor product, to, let's say V tensor V star, and this will send, well, since it's linear, I only need to tell you what it does to 1. So this will send 1 to the sum I equals 1 to n of I tensor I, and epsilon is going to go from V star tensor V to C. This is going to send J tensor, backwards, J tensor I to Ji. And you can check for yourselves that these identities are satisfied. And so in contrast to the case in set, we canonically get duals for every object in finite dimensional Hilbert spaces. And I encourage you also, so as I mentioned, I'm not going to really go through the example of REL in any detail here. I encourage you to try and interpret all of what we do today in REL as an exercise. It is the best way, I think, to quickly understand the kinds of structures that we're playing with. Everybody happy with this? Okay, so now let's try to prove some things using Hilbert spaces. And I'm actually going to stay on this board because I want to keep the definition up. Or not Hilbert spaces, using string diagrams. So first, let's try the following lemma. If L is dual to R via eta and epsilon, and L prime is dual to R via eta prime and epsilon prime, then L is isomorphic to L prime. Duals are essentially unique. So we're going to define F from L to L prime as follows. Well, we want to start from L, which means we need an L here. And so we're going to put epsilon here, and here we get R. And here we'll put eta prime, and we'll get L prime out. And we'll define G that goes from L prime to L in basically the same way. Epsilon prime, L prime, R, eta, L. And now we just need to prove that these are inverse to one another. So I'm only going to focus on, let's say, f of g. This is going to go from L prime to L prime. I should have chosen the other, but whatever. Okay. So we have L prime R eta L epsilon eta prime L prime R. And now we're going to rearrange this. Epsilon prime eta epsilon eta prime L. So now we have this nice little chunk in the middle, but by our relations, we know that that chunk in the middle is just an identity. And by our relations again, we know that this is just an identity. And we're done. That is the proof. I mean, technically you have to show that the other composite is the identity, but it's the same argument. Once again, I think that this graphical language is extremely nice because it allows you to take things that you know, represent them pictorially, and manipulate them in a very intuitive way. So actually, maybe let me add the little box for done. Okay, so what about when we have dual objects in a symmetric monoidal category? After all, that's what we're really interested in. And then we might very reasonably ask, well, can we say that, for instance, if L is left dual to R, then R is left dual to L? Does this work? Does the symmetry preserve duality? Well, once again, I guess I need to start on this board again since... So, once again, the pictorial argument makes a lot more sense than the symbolic one. So let's try and put that into practice. Let C tensor I be an SMC, then L is left dual to R if and only if R is left dual to L. So as a proof, we say L left dual to R with duality data and so then we'll define eta, where now we want LR to be, well, we start from our duality data, and then we twist. And epsilon RL, again, we start from our duality data and twist. And now we need to verify that these two relations hold. So once again, I'm only going to do one of them, but that should hopefully be enough to convince you of the validity of the argument. So here we have R, L, R, and then we're just going to expand out the definition. This is R I should probably make sure that my arrows are pointed the right way. That's good. Okay. R, L, R. Well, but now I can drag things around so long as I'm not reordering the objects, but there's nothing to reorder. So this is R, L, R. And then we apply these snake relations to this interior, and we get the identity. Once again, this is rather a lot nicer than trying to reason through why this works using a more symbolic notation. Okay, so does anybody have any questions about making arguments or making definitions with string diagrams? Because the last thing that I want to do today is not as much related to what we previously did, It's just going to give a definition that's going to come up a little bit later. And I wanted to give it partly because it's one of the things that Selman mentioned in his motivating talk. And so it would be nice to see how it is expressed. Any questions? Okay. So I should also say, per this lemma, when we're working in a symmetric monoidal category, we will often just say A is dual to B. And we won't mention the duality data, even though it is there. We'll be assuming a choice like this and this, but then we also get then a canonical choice of duality data corresponding to just twisting those duality data, showing that, say, R is left dual to L. And then we'll just say the objects are dual. So let A and A star and B and B star be dual objects in a symmetric monoidal category C tensor I. And here I'm going to have to look at my notes because I always get which one of these is the dual of the other mixed up. I should say, one can also, in this case, take that A is left dual to A. If we're not in a symmetric monoidal category, this definition will still work. But I don't think we're going to consider it any less generally than that. So given F from A to B, the name of F is the morphism F from I to A star tensor B given by so let me think for just a moment, or actually I can just look at, yes. A star B F, this is the name of F. And the coname of F is F from, now this should be B star times, let me double check. A times B star, of course, okay. A times tensor B star to I, given by F goes from A, B, B star. And this is, again, coname of F. Now, it's worth noting here that the name of F uniquely determines F, and the coname of F uniquely determines F. Can anybody suggest a string diagrammatic reason why? Yes? Yeah, if you know the coname, and you compose it with the piece of duality data, you get F back. And similarly for the name, you use the other piece of duality data. So these really do uniquely determine F. Okay, so this is what I wanted to get through. I would very strongly encourage working out each of the concepts that we've discussed in the category rel so that you have a grasp of how to work with them. And I would suggest in finite dimensional Hilbert spaces spending a little time working out the name and coname of a specific morphism. I promise it will not be time wasted. Okay, are there any questions before I end?
Maybe a small comment.
Yeah.
Two lemmas that you wrote before imply double dual fundamentalized one.
Yes.
Yeah.
Yes, they do. Absolutely, yes. So I mean, in general, I chose these two because they are useful, but I wasn't really trying to make a particular point about dual objects yet. I think that later on we'll see a little bit more structure on dual objects. But rather, these are just illustrations of how you work with string diagrams. But yes, you're right. It does show that the double dual is not just isomorphic, but canonically isomorphic to the original. Other questions or comments? Okay, then many thanks.